Hello and welcome back. So we're going to start doing some mathematical examples of the pigeonhole principle. The previous ones are more fun, real-world examples, which are engaging, and some of them are simpler and help you get your hands around it. Some are more complicated, but it's more real-world, so there's a dimension to it which is easier to grasp. Nevertheless, we're now going to start moving into some more mathy examples. For a couple of the examples that are going to be coming up, I'll need the whole board, I anticipate. So I moved the principle down here on this little sideboard. Hopefully you can see it. It comes in two forms. This is just the shorthand, so you can look back at your notes to see the formal statement of the pigeonhole principle. But here it is in shorthand. If you have n plus 1 objects going into n boxes, then what are you guaranteed? You're guaranteed that you have a box, at least one box, that contains at least 2 objects within it. The general form, if you have kn plus 1 objects being placed into n boxes, then you are guaranteed to have a box with at least k plus 1 objects within it. Okay. So, proposition 1.9 in my proofs book is this. Given any 5 numbers from this set, the set 1, 2, 3, 4, 5, 6, 7, and 8, so given those 8 integers, if you pick any 5 of those 8 integers, you're guaranteed that 2 of the 5 numbers that you chose add up to 9. That's interesting. Probably not something you've thought about before, but it's interesting. So, one of the challenges with the pigeonhole principle is deciding what are my objects and what are my boxes. It's a little less obvious here. What should your objects be? What should your boxes be? That would guarantee to have 2 numbers add up to 9. So it does mention 2 numbers at the end. The simple form of the pigeonhole principle, the conclusion involves 2 objects. So that's at least suggestive that the simple form is going to be the one that we're going to use. But maybe not. I don't know. So pause the video, look at this, and see if you can think about what would your objects be, what would your boxes be, and how would you use the principle to write it out. So go ahead and do some scratch work and see if you can figure that out. Okay, so if you did it, congratulations. If you didn't, what I suggest is to do some examples. Examples are a really good way to understand what's going on, and oftentimes examples sort of show you why something is true. You didn't have to prove that it's true. You have to maybe use the pigeonhole principle or something else to actually prove it. But you can at least understand why it's true. And as soon as you understand why it's true, you're on the path to proving it. So let's do it. So I have a random number generator. So I'm going to generate some random numbers, 5 at a time from the set from 1 to 8. And I'm going to write them up on the board, and we'll see if the principle holds. Okay, the first 5 it gave me are, they're out of order, 1, 2, 5, 6, 7. So if the numbers are 1, 2, 5, 6, and 7, do you see 2 numbers which add up to 9? Yeah, 2 and 7, I think, add up to 9. 2 and 7 add up to 9. So there you go. So this set of 5 numbers did indeed have a pair which added up to 9. Let me run this again. Oops, sorry. Okay. It is giving me 1, 3, 4, 6, 8. 1, 3, 4, 6, and 8. Do you see a pair of numbers which add up to 9? Yes, 1 and 8 add up to 9. Also 3 and 6, by the way, add up to 9. So that could happen. Could be the case that you have 2 pairs in it. But we have 1 and 8 adding to 9, and also, by the way, 3 and 6 adding to 9. Okay. And you should do this a few times on your own. Maybe I'll do it just one more time. And this time I'm getting 2, 4, 5, 6, 7. 2, 4, 5, 6, and 7. And looks like we have 2 and 7. Also 4 and 5. So we have 2 and 7 and 4 and 5 adding up to 9. Okay. So you might get 2 pairs. If I did it 3 times and I got 2 pairs twice. That's interesting. Okay. So what does this tell you? If you did a few more examples on your own, then you have a few more sets to add to this list. Do you have any ideas? So something that I might try is to think about what are the possible ways that you can get 2 numbers to add up to 9 from this set. Well, let's see. We have 1 and 8 could be one way to get to 9. 2 and 7, 3 and 6, and 4 and 5. So these are the different ways, looks like there are 4 of them, in which you can have 2 numbers add up to 9. Okay? Is this ringing any bells in your head? Any ideas? Yeah, I mean, this is looking interesting. So if we want to use this simple form, we have objects and boxes. What should our objects be? Well, we're going to be given 5 numbers. It's reasonable that you're given 5 things. It's like we were given, n plus 1 socks. Those are probably the objects that we have to put into boxes. So using the 5 numbers as our 5, it would be 5 objects. So n would be n plus 1 would be 5. That makes some sense. And that's great because you need more objects than boxes. And right here we have a list containing 4, right? So maybe these somehow could be our 4 boxes. Do you see? So I think this is the way forward. So we have 5 given numbers. These can be our 5 objects. And we're going to put those 5 objects into 4 boxes. And the simple form of the pigeonhole principle would say we'd be guaranteed in that circumstance to have 2 of these 5 objects end up in the same box. So all we need to make sure is that the boxes are like 1 box for 1 and 8, another box for 2 and 7, another box for 3 and 6, another box for 4 and 5. Does that make sense? So those are 4 boxes. Every time you get a number, if you get the number 7, you put it in the second box. If you get the number 4, you put it in the 4th box. If you get the number 5, you also put it in the 4th box. And doing it in this way, you're guaranteed that 2 numbers will end up in the same box. And as long as they're in the same box, the 4th box, the only numbers that are going to get put in there are 4 and 5. So if you have both of those numbers in the same box, then you have a pair of numbers which does indeed add up to 9. Make sense? Okay, so let's write this up. Proof. So let's consider these boxes. So there's going to be 4 boxes. 1 box with the numbers 1 and 8 written on it. Another box with the numbers 2 and 7 written on it. Another box with the numbers 3 and 6 written on it. And a 4th box with the numbers 4 and 5 written on it. So if you get a number, you get 5 numbers, put each number into the box with its label. We're guaranteed that 2 numbers are going to be in the same box. If those 2 numbers are in this box, then those 2 numbers have to be 1 and 8, which add up to 9. If those 2 numbers are in this box, those 2 numbers have to be 2 and 7. Oh, great, add up to 9. Same thing with these these last 2. Okay, so given, consider these boxes. Let the 5 numbers, or 5 chosen numbers, be our 5 objects. So we've identified what are our objects, what are our boxes. That allows us to apply the pigeonhole principle directly. Place each object into the box with its label. So find the box which has your number, whatever number you just chose, has that number labeled on it, and that's the box where you put it in. By the simple form of the pigeonhole principle, simple PP, at least 2 numbers. And remember, I gave this monologue last time about how PP, that's great for your notes, simplifying your pigeonhole principle down to 2 letters. Good for your notes, good for board work, not good for formal solutions. So when you write up your homework, you should actually write out pigeonhole principle. Guarantees at least 2 numbers must be in the same box. And by construction, each box, the 2 numbers in it add up to 9. So these 2 numbers add to 9. And a box signifies that our proof is done. So there you have it. That is another pigeonhole principle example. In it, we were given 5 numbers from a set of 8 things. We want 2 of them to have a certain property. So we turn the 8 things in the set into 4 boxes. We make sure that each box, the only time 2 numbers can be placed in a single box is if those 2 numbers add up to 9. That way, 5 things going into 4 boxes guarantees 2 things are in the same box. And because they're in the same box, by the way we set it up, that means they add up to 9, and boom, there you go. Apply the pigeonhole principle, and you are done. Okay, so that is the first example. How long is this recording? 12 minutes. Okay, yeah, I think we'll stop here. So this will be one video, and then in the very next video, I'll do yet another example of using the mathy example of using the pigeonhole principle. Okay, see you for that one.